So the next topic we're going to talk about is complex ion equilibria. And we're going to work the last example problems in this chapter, the example problem and the formal practice problem. So our first problem states that you mix a 200 milliliter sample of a solution that is 1.5 times 10 to the minus third molar in copper nitrate with a 250 milliliter sample of a solution that is 0.2 molar in ammonia. After the solution reaches equilibrium, what concentration of copper remains? So you can look up that this complex forms right here. The copper plus the ammonia forms the complex, and the K sub F for that formation is 1.7 times 10 to the 13th. So we need to calculate the new concentration of copper in solution, and we can do that by multiplying the molarity of the copper solution times the volume that we used, and we get the moles of copper. And we divide that by our new volume of mixing. So we mixed a 200 milliliter plus a 250 milliliter sample. And when we divide by the new volume, we get our molarity of copper as 6.7 times 10 to the minus 4. We can do the same thing for ammonia. Mix the molarity of the ammonia solution times the volume of solution and get the moles of ammonia. Divide by the new volume after we mixed it, 0.2 liters plus 0.250 liters, and we get 0.11 molar. Now we need to construct an ice table and plug these new concentrations into our ice table so we can calculate how much we have at equilibrium. So we were asked to find the concentration of copper remaining. Okay, so that means at equilibrium. So let's plug our concentration of copper here and our concentration of ammonia here. Right, and so what we see here is that the ammonia at equilibrium, okay, is going to be 0.11 minus 4 times the amount of copper that we lost. Okay, so we're losing 6.7 times 10 to the minus 4, so essentially all of the copper. And the reason is because our Kf is so large. So since our Kf is so large, we can assume that this system essentially lies to the right. So we're losing essentially all of our copper. Okay, and we're going to lose 4 times that amount of ammonia, and we're going to form that amount of our complex because we've got a 1 to 4 to 1 ratio in our equation. Now, if we go ahead and let the amount of copper remaining equal X, we lost almost all of it, but essentially all of it, but we're supposed to calculate that minute amount that remains. And I went ahead and subtracted the 4 times 6.7 times 10 to the minus 4, that ammonia amount, from the initial ammonia amount because I didn't consider it to be insignificant. Now, your book is saying here that it's basically insignificant, but I went ahead and calculated it. So 0.11 minus 4 times 6.7 times 10 to the minus 4 for our ammonia at equilibrium. And then we gain 6.7 times 10 to the minus 4th of our complex. So at equilibrium, if we say our copper is equal to X, our ammonia is equal to 0.11 minus what we lost. We lost essentially all of our copper, and we lost 4 times that amount of ammonia. So 4 times 6.7 times 10 to the minus 4th. And then we gain that amount of our complex. So for every mole of the copper that we lose, we gain that amount of complex because it's a 1-to-1 ratio. So we're gaining 6.7 times 10 to the minus 4th. So let's set up our Kf equation. We've got products over reactants from our balanced equation. So we get our complex over the copper times the ammonia. Now we're going to let our copper equal X and our ammonia, we're going to go ahead and plug that amount in, okay? So I went ahead and did it a little differently. I said, okay, the complex is going to be 6.7 times 10 to the minus 4th. The copper is equal to X, and then I went ahead and subtracted this amount from the ammonia because I didn't consider it to be insignificant. All right, and so that is to the 4th because we have a coefficient of 4 there. And if we solve for X, okay, because our K is 1.7 times 10 to the 13. If we go ahead and plug that in and solve for X, then we get X is equal to 2.882 times 10 to the minus 13. So that's the amount of copper remaining after after essentially the complex forms. Now your book got a slightly different number because they considered that the amount subtracted from the ammonia was insignificant. All right, so we're going to go ahead and work an example here, the 4 practice problem.